This is part 3 of chapter 9 of machine design 1. Today I will solve the remaining problems including bending that we have not done until now, and also we will be solving some design problem as well. So starting with the first problem of today, this problem is exactly same as we have done last problem in the last class. In that problem we had only torsion T applied externally, but in this specific problem we have also a force of magnitude 8 kilonewton applied vertically. So now we have force, torsion, and torsion, and this will cause all three stresses at this end. We will assuming that the weld is made here. This whole circle is a weld. So due to this force and this torque, we will be having some stresses, and we will be calculating stress. Due to this stress, we will be calculating what is the maximum stress. As the question, they have given us maximum allowable stress. Once we have maximum stress and the weld size is unknown, so the maximum stress will be as a function of H. So we will be comparing applied stress with allowable stress, and the final answer will, in the final answer we will get the value of H, or weld size. So starting from for the problem, this specific problem, if you see, we have F force. This force will cause primary shear at this surface. This torque will cause secondary shear, and this F will cause bending, which is a tertiary shear on the surface. So calculating primary shear, the equation for primary shear is tau prime is equal to F or V, F by A. F by A. What is F? Magnitude is given 8 kilonewton. And what is A? 2 pi r, length into size. 2 pi r into size. What is the size of weld? 0.707, but for weld we will be using throat thickness, so it is 0.707 H. So this is the final value. If you substitute all the values, because R is known, 50 mm dia, so R is 25 mm, H is unknown, so the final answer we will get is 72.036 divided by H kPa. So this is a primary shear. The second part is to calculate secondary shear. For secondary shear, first of all we need to check which category of secondary shear it belongs to. This is a circular weld, so the last figure in table 9-1 is circular. So getting data from there, the magnitude of secondary weld is tau double prime is equal to TR by J, because this is torque and we have the value of torque. Torque is given, R is 25, and for J, TR divided by J is 0.707 HJU. And for circular weld, from table 9-1, get the value of JU, substitute the value here, which the value of J is 2, JU is 2 pi r cube. So the answer will be T, which is 2000, R is 25 mm, H is unknown, and JU is 2 pi r cube. We have all the values. Substituting values will give us the value of secondary prime, which is equal to 720 by H. Units are kPa. The third part, this force is also causing a tertiary shear on this surface. The bending, in simple words, it is bending. Why it is bending? Because due to this force, this point of cylinder will try to come out of the plane. So the equation of tertiary shear is M R by I, and value of M is F multiplied by moment arm, which is equal to F is the magnitude of is 8 kilonewton, and moment arm is 150. Kilo and millimeter are cancelled, so we have the SI unit of 8 into 150 divided by I is 0.707 into IU from table 9-2 multiplied by H. I missed H. From table 9-2, the last figure is circular weld for bending. The value of IU in that table is pi r square. So we have all the values. Substituting value will give us the value of tertiary shear equal to 864 divided by H kPa. Now we have primary shear, we have secondary shear, and we have tertiary shear. We have all the shear values. Just changing the color. We have all the shear values. We need to calculate resultant. And what is the resultant in this case? For example, in this case, we know that maximum bending is at the top. The secondary shear is equally distributed at all points. At all points, the secondary shear is equally distributed. At this point, secondary shear, direction of secondary shear is in this direction. If you have axis, it is parallel to this axis. The secondary shear is parallel to this axis. Tertiary shear is parallel to this axis, and primary shear is parallel to this axis. We have all three perpendicular shear stresses: primary, secondary, and tertiary. To get the magnitude for using vector tau max is equal to square root is, it is a simple equation of square root of calculating tau prime in x direction plus tau prime in y direction plus tau prime in tau prime in x direction, tau double prime and tau triple prime, all three in x direction, square, then square of tau prime in y direction, tau double prime in y direction, tau triple prime in y direction, plus square of tau double prime in z direction plus tau double prime in second and tau triple prime in z direction. But in this specific case, all three are perpendicular to each other. So in x direction we have only one, which is equal to, we will just write tau prime square plus tau double prime square plus tau triple prime square. We have each shear stress is in one single axis, so we don't have any sine or cos value. So substituting all the values 864, 720 and 72, substituting here, we will get the final value. I have not calculated final value, I have just used this value as I will be using. It is 120 MPa into 10 raised to power 6 equal to tau max, and substituting all the values, the 1 by h is common, so 1 by h will be common. 1 by h square under root is 1 by h. We have 72 square plus 720 square plus 864 square. To be on the safer side, this allowable stress should be more than the maximum stress. So this has to be, the equation has to be like this. If tau maximum is greater than this value, the structure will fail. So this has to be greater. So substituting all the values, we will get the h will come here and 120 will come here. So solving for h, the final answer will be h should be greater than or equal to 9.39 mm. So in this case, the size of weld should be more than 9.39, or we can say that it has to be equal to 10 mm for a safer weld. So this weld will be safe if the weld size is 10 mm. This is the method of solving combination of primary, secondary and tertiary shear problems. This second problem is problem 9-9.48. It is concerned with weld, bracket weld. You see this, the force applied here, weld is done here, so it is a type of tertiary weld or a case of bending. What we need to do? Figures show that the welded steel bracket loaded with static force F, we have F. Estimate the factor of safety if the allowable shear stress in the weld throat is well. So we have the value of tau allowable 120 MPa, and we need to calculate factor of safety. Magnitude of F is also known. So this is a case of bending, starting with primary shear. The magnitude of primary shear is tau prime is equal to V by A. And what is V? V is 7.5 kilonewton. And after what is the area? Length, length, length. So 120 plus 120 plus the size of this is 60. So 240 plus 60, 300. And multiplying 300 with area is equal to V is equal to 7500 into 0.707 H into 300 into 10 power minus 3, because the units are millimeter. So tau prime is 5.892 MPa. This is also the easy part. Now the actual part is to calculate. The second part is to calculate bending stresses or tertiary shear in this case. First of all, we need to check if this figure corresponds to any existing figure in table 9-2. Go to table 9-2, check the figure, and out of these figures, figure 5 matches this description. Figure 5 is similar to this one. In that figure, if you see that the figure, we have a value of 120 mm is vertical column in that figure 9-2, figure 9 table 9-2. This figure vertical column is given as D and 60 mm is B. So 60 mm is B and 120 mm is D. To calculate value, to check the value, area can be, this area can also be calculated from that table, this area. The first factor in that table 9-2 figure 5 is this value. So we have area from that. Also, we need to calculate X bar and Y bar, the value of X bar and Y bar. And this X bar is from this top, this surface. So X bar is half of B, which is equal to 30 mm. And Y bar is equal to D square by 2B plus D. D square divided by B plus 2T. We have the value, substitute value there. This is D, this is D, and this value is B. We have the value, substitute value, will get the Y bar equal to 48 mm. So the centroid of this plane lies at 48 mm from the top. And this distance, how much is this distance? 120 minus 48 gives us this distance, which is equal to 72 mm. Now we need the value of IU, because this is bending. The value of IU, the value of IU from table 9-2 for this specific case is, can be seen, it is equal to 2D cube by 3 minus 2D square Y bar plus B plus 2D Y bar square. What is Y bar? This is 48 mm is Y bar. So we have all the values. Substituting value will give us IU, which is equal to 4.608 into 10 power minus 4 cubic meter. And value of I is equal to 0.707 IU, which is equal to 1.955 into 10 power minus 6 meter 4. So we have I, we have X bar, Y, we have tau prime. And to calculate bending moment, what is the magnitude of bending moment? M is equal to F into moment arm, which is equal to 120 mm into 7.5 gives us value of 900 Newton meter of bending moment. So we have all the values. Tau triple prime is this case equal to my by I. What is M? 900 mm. What is I? Which is I is 1.955 into 10 power 6. And what is Y? Y is the largest distance of the edge from this O. The distance is not 48, it is equal to 72, because 72 is the largest distance. So maximum bending moment is here on the bottom edges, not on the top edges. So 900 into 72 mm divided by I, substituting all the values, will give us the value of tau double prime equal to 32.23 MPa. We have the primary, we have tertiary shear. One thing is to remember that when we have let me explain. When we have bending, torsion and primary shear is downward, torsion this. So we, in that case, we have to calculate resultant, and that resultant has to be calculated from x and y component of both. Because if the case is like this, let's suppose this is center, this is the largest distance, this is secondary shear, and primary shear is either horizontal or vertical downward. So in that case, if we need to calculate the resultant, we need to check from the components, x component of this and y component of this. We need to get square of x component of all plus y component of all. But in case of bending, because bending is like this is out of plane, the weld is made here, so primary shear is within the plane and this tertiary shear is always out of the plane. So this, they always make an angle of 90 degree. If we have a case in which we have primary shear and secondary shear and tertiary shear, primary and secondary shear makes and that all three are not perpendicular. In that case, from primary and secondary shear, we have a result, we get a resultant. That resultant is in the plane, and anywhere in the plane, this tertiary shear will always be perpendicular to this resultant. So if we have case of 3, we need to calculate resultant of primary and secondary, and then from that resultant, tau square plus tau triple prime square under root gives us maximum tau in the weld. So this is the method of calculating. But in this case, we have only a case of primary and tertiary. So to calculate tau max, we only need, because we know that primary is uniformly distributed everywhere and tertiary is maximum here. So maximum resultant will be at this or this end. So tau max is equal to square root of tau prime square plus tau triple prime square. Substituting values, we get tau max equal to 32.76 MPa. We have maximum allowable stress is given. So check the factor of safety. Factor of safety is equal to tau allowable divided by tau m. 120 divided by 32 gives us factor of safety of 3.66. So in this case, our weld is secure by a value by a factor of 3.66. These two problems are related to design problems. So you need to understand the methodology. You need to understand which weld is the best option for in the case of torsion and which is the best option for the case of bending. In this example, they explained that table 9.1 is concerned with primary shear, secondary shear or torsion. For that, they have given us a figure of merit. To check figure of merit is J divided by volume. This is the volume of weld and this is J of weld for all the weld, because 0.707 JU is common. So substituting the value, we get a generic equation of JU by HL, or in other words, FOM is directly proportional to JU by HL. This value will give us which of the 5 secondary shear or torsion and I think 9 tertiary shear welds, which is the best option. So in this problem, they have just asked to rank the welds in torsion weld in table 9-1 according to their FOM, figure of merits. We have this value. The equation that we have to use is JU by HL. We have JU. Substitute. One thing I missed. They have told us that there is a space of area A cross A space. A cross A space. And square of A cross A. For this A cross A square, which is the best option of weld that we can use? So in this case, this maximum height is A. In this case, maximum value of D is A and maximum value of B is also A. In this case also, these values are A. Similarly, in this case, maximum value of D is equal to A, maximum value of B is equal to A, maximum value of D is equal to A, maximum value of B is equal to A, and in this case, diameter is equal to A, or in other words, R is equal to A by 2. So we have a square area where we can weld. The area of square is A cross A. We have all the values. We have value of Ju. So this value will become A cube by 12 divided by HL will give us value. Substituting all the values. Oh, and also, if we have, what is L? L is the length of weld. For this weld, for this specific weld, let me change the color. For this weld, what is the length? Length is equal to A. For this weld, length of weld is equal to A plus A equal to 2A. For this weld, length of weld is equal to A plus A equal to 2A. For this length is equal to 3A. For this weld, length is equal to 4A. For this weld, length is equal to 2 pi r. These are the lengths of weld. This is the equation. Value of Ju, A cube by 3 divided by H into L. H is unknown. L is equal to A. Substituting value, this we will get the value equal to, substituting value we will get FOM prime at Ju by L, or equal to 0.0833 A square by H. If we substitute same value for here, we will get FOM prime. Just use A square by H equal to C. This term as C. So for this FOM prime will be equal to 0.333 C. For this FOM prime is equal to 0.2083 C. Similarly, for this case, a substitute value, it is equal to 0.3056 C. FOM prime for this case will be equal to 0.333 C, and FOM prime for this specific case is equal to 0.25 C. Once we have FOM prime values for R, now we have to rank the value. The value with highest figure of merit is the best option to select. So if you check the value, which value of FOM prime is highest? Dark blue. 0.333 in this figure is higher, and here also 0.333. So rank of this value is 1. And this also has a rank of 1 first. What is the second value? Out of this, the second value is this is the second rank value. Third rank value is this 0.25. Then we have this value, and the last value is this. So if you have an area of A cross A, this figure 2 and 5 are the best option of weld that you can have on that surface. The second best is 4, third best is 6, fourth best is figure 3, and fifth best is 1. So when you have design problem and you have a specific area, just you can, the first choice of your first choice can be figure 2 or figure 5. Figure of merit is same. Why it is same? Because just let me explain. Because this is case 5 and this is case 2. Here we have, if you compare this, we have double the length of weld and double the volume. It means double the value of Ju. So value of Ju is doubled and value of L is doubled. Due to that reason, the figure of merit is same. So it is only the case that if you put 2 extra weld here, the strength per unit length, if you neglect it, strength per unit length of weld is same for both these cases, in simple word, in case of torsion. So this is the method of selecting type of weld. Same goes for bending. In bending as well, we have a figure of merit, IU by HL, exactly the same. We have an area of A cross A. We have an option to put all the welds, again using exactly same method, substituting the value to calculate figure of merit. This you can do it yourself as well. The value of first is 0.833C, the value of FOM prime. The value for second figure is 0. Sorry, 0.8, not 0.08, 0.0833C. Again, in this case, it is equal to 0.25C. For this case, this is equal to 0.1944C. In this case, we have case number 5, we have 0.11C. For this case, we have 0.1667C. For this case, we have 0.11C. Two figures are remaining. For figure 8, the value is 0.1667, and the last circular one, it is equal to 0.125. When we are required to rank these values, just let me write the rank as I have already written in my book. So rank is rank 6, rank 6, rank 1, rank 2. For fifth one is rank 5. This is rank 3. This is rank 5 again. This is rank 3, and it has a rank of 4. So if we have a case of bending and we have a cross-section area of A cross A, then the best choice to use is this parallel weld. So, and this square weld is at rank 3. So if you see the previous case for bending, this specific case, this all around square weld and parallel weld had same rank, first rank, but for bending this has the lower rank. So if you have a case of multiple welds, if you have a case of bending plus torsion, then the best option is to use a parallel weld, which is case 3, and not parallel. This parallel, horizontal parallel weld. Vertical parallel has a rank of 6. Horizontal parallel has a rank of 1. So this is the best option to use in case of bending. But when you have a problem, when you have a specific problem, to solve that problem, you have to check, you have to select a weld. So you can go for any weld, select that weld, select an electrode, and solve the problem for a safe weld. Once you get the answer, just check if your answer is feasible or not. If it is feasible, your selection was good. If it is not feasible, you have to select another weld. That method I will explain in the coming problems. We have two design problems to solve, and after that the class will today's lecture will be ended. Starting from problem 935. For this problem, this is a case study. Attachment 12. We have a 12 kilonewton of external force. Attachment length is L1 is equal to 225. So the total length is 225 minus 150. The remaining length is 75 mm. And dia is also 75 mm. So it is also 75. So we have a square area of 75 by 75 mm. Specify the weldment. So what you need to specify the weldment, give the pattern, which pattern has to be used, which electrode has to be used, and which type of weld has to be used, how much should be the length of weld, and what is the leg size. All these requirements are the requirement. So what is this case? This due to this case, this force, the bar will be rotated. So this is the case of torsion. So we are in case of torsion. So for data we are required to go to table 9-1. So what we need, just go to table 911 and which type of weld you required to do. The first rank, the rank 1 was either for figure 2 or figure 5. Here I start from case 2. parallel weld. I will assume that we will putting a weld here and here because it had a rank of 1, FOM1. So selecting this weld, the centroid will be at the center, exactly center. You can go and check the value in table 9-1, and this value is 75 by 37.5, 37.5 from the edges. So we have the value, and the maximum shear will be at any edge. To area, if you go to table, you can just check the area. This is 2 times length into 0.707 h. So 1.414 into h into this length, which is equal to 75 mm. So the final area, if we substitute all the values, the value of area is 106 h. So this is the area of this weld. Secondly, we need to check the value of J. J is equal to 0.707 J U into H. For value of JU, if you go to table, the value of JU is D into 3B square plus D square divided by 6. We have all the values. We know what is D, we know what is B. In this case, it is square. D is equal to B. We have the same value in this case. So substituting value, we will get a value of J equal to 198.8 into 10 power 3 H mm 4. We have J, we have A. Because this is 75 by 75 area, so this angle is 45. Understood? This angle is 45 degree. There is another method to solve this problem. Either the first method that we have done till now is that we calculated this R by angle, we calculated R. Then to calculate the magnitude, we use a value of let's say tau double prime cos theta square plus tau double prime sin theta plus tau prime whole square root will give us a value of tau double prime. But we can just solve for the x and y. For example, if you take this value, we know that this is 37.5, and due to this force, secondary shear is tau double prime y, and similarly for this moment arm, this is tau double prime, let's say it is x. Similarly, the primary shear is tau prime x. It is distributed, so it is very easy to just get the value of tau double prime x and tau double prime y. As we have same R, so the value of tau double prime is equal to mr by j. If we get tau double prime x equal to tau double prime y is equal to, instead of R we use 37.5. We have moment here, which we will calculate, and j is the same, so we will get same value for tau double prime x and tau double prime y. In this specific case, it is same. Otherwise, if you have different value of R, just substitute value and get the value of tau double prime x and tau double prime y. What is value of m? Value of m is force divided by moment into moment arm, which is equal to 150 plus 35, 185. We have 37.5. So 187.5 is moment arm. Force 12 kilonewton into 187.5 will give us a moment of equal to 2250 Newton meter. We have moment. We have R. Just substitute moment. We will get the value of 424.4 divided by h. And similarly, tau prime is equal to V by A. Force is equal to 12,000 divided by area. This value of area, use area here, and the primary shear will be equal to 113.2 by H. So just check the value, either it is MPa or KPa. I have not written the unit, so it can be KPa as well. So just check this value, MPa or KPa for this. To check the resultant or tau max in this case is equal to tau prime plus tau double prime x whole square plus tau double prime y square. Substituting values, tau double prime x and tau double prime y both have the same magnitude. Substituting value will give us tau max equal to 684.9 by H. Allowable stress, what else is given? Material is given. So we have knowledge of material 1018 hot rolled, 1018 hard. Both the materials are made of 1018 hot rolled steel. So check the value of 1018 hot rolled steel from table A-20. The value of S yield is equal to 220 and S ultimate it is equal to 400. So what is the tau allowable? Tau allowable is minimum of 0.3 S ultimate or 0.4 S yield. Substitute to both value. 0.4 of S ultimate is 160 and 0.4 of 220 is 88 and 0.3 of S ultimate is 120. So we will be using 88 MPa. This is our tau allowable. Compare this tau allowable with this value. We have to compare these two values. 684.9 by H should be at least less than this value. Should be less than this value for a safer structure. So substituting that value, then H will be value of H should be greater than or equal to 7.78 mm in this case, or we can say 8 mm. What is the thickness of plate? 12 mm. So on thickness of 12 mm, 8 mm size weld can be welded. So we will be using this as a final answer. So if the weld size is 8 mm, length of weld, leg size, we have size of 8 mm, length of weld is 75 plus 75, 150 mm. You can give the remaining also here. H is equal to 8 mm, length size is 150 mm. Type of weld is parallel, case 2, table 9-1. Electrode number. So the last thing is to check the electrode number. In table 9- I think it is 9-3. In table 9-3, check which electrode has higher strength as compared to this strength, S by 220 and S ultimate 400. All the electrode have higher strength, so we can use any one of electrode, but the one with the least strength will be cheaper. So we will be using electrode E60XX, which has an yield strength of 345 and ultimate strength of 427. So this is the selected electrode for this specific problem. So this is how we solve design problems. I know that the lecture is becoming long, but this last problem is one of the most important problem to solve. And after that, this chapter will be ended. For this specific problem, what this is also a case of torsion because load is applied here and weld is made here. Weld is made here. Due to this force, in the question, they asked us that the size of the width of this column is given, which is of no use. The width of this column is given as 25 mm. Static load is given as 8 mm. The clearance, minimum clearance required is 160 mm, 156 mm. The more clearance is possible, but minimum has to, a minimum is given. The attachment and the column both are made of 1018 hot rolled steel. So this and this, both of them are made of 1018 hot rolled steel. What we need to calculate, we need to check, give a pattern. We need to give an electrode type, type of weld, length of bead, all the things that we have already done. And also we need to give a length L1. Length L1 means this value is not given. So this value is not given. So we have to assume some values to get the final values. So this is the given data. For this specific problem, all the given data I have all, to save your time, I have already typed most of the data. Given data is both the material are made of 1018 hot rolled. So from table A20, check the value of SY and S ultimate, and from these values we have we should have from this value what is tau allowable. It is either 0.3 of S ultimate or 0.4 of S yield. It is exactly same data as the previous problem. So the tau allowable is 88 MPa. Similarly, what is the electrode that we can choose? Any electrode with SY more than this and S ultimate more than this can be used. If you go to table 9-3, all the electrodes have higher strength. So again, using electrode E60XX. So this electrode we have chosen, this is a tau allowable that can be applied. Type of weld. Then now the third thing is which is the type of weld that we can use here. Depending on figure of merit, in table 9-1, type 2, case 2 and case 5 both can be used. Just like previous problem, we will be using a type of case 2. Case 2 parallel weld. So this tau allowable, exactly same equation I have written again, there is no need. So now we have selected case 2. For case 2, all remaining data of case 2 you can use here. For example, area, weld area, the equation of area for case 2, because case 2 is parallel weld. This parallel weld is case 2, and area is given as 1.414 HD, and this is D in this case. This value is unknown. Just assuming that if this length is 150, assuming that this D is also 150. This is our first choice because data is not given, so we can assume some values. If this D is 150, just substitute value 150 plus 150, 150 to 1.414 into H, we will get value of area which is equal to 212.1 H mm square. So we have area. This value is also 150. So this is square weld. If this is a square weld, the centroid lies exactly at the center, or you can just check the value from case 2 as well. So if this value is at the center, we can just use exactly same method. This is tau double prime X or tau double prime Y, and primary shear tau prime is equal to F divided by area. F is equal to 80 kilonewton. 80 kilo divided by this area. Substitute value, you will get primary shear equal to, where I have calculated, 377.2 H. this is the value of primary shear. So this is primary shear will be acting at all the points, uniformly distributed. This value and this value are same exactly as we had already. So primary secondary shear x is equal to secondary shear y, which is equal to moment into mx by j, or equal to my by j. Take this distance as y and this distance as x. In this case, y and x both are same. Y is equal to x, which is equal to half of 150 is equal to 75 mm. So this value is same. To calculate m, what is m? M is equal to F 80 kilonewton multiplied by moment arm. So taking this value as the minimum value of 156 plus 75, because center is here. So value of 150, half of that value is 75. We have m equal to 18.48 into 10 raised to power 6 Newton millimeter. We have m, we have all the values. We need j as well. J is equal to 0.707 HJU. Just check the value of JU from table 9-1. The value of JU given in that table is, I have just substituted the value. Just let me check. The value of JU is D into 3B square plus D square whole divided by 6. So substituting values, the final answer of J is equal to 1.59 into 10 raised to power 6 H mm square, mm4, sorry. 1.59. We have J, we have M, we have XY. Substituting these all values, we will get the answer will be 871.7 by H. Calculate the resultant. Where is the pen? Yeah. Tau max is equal to tau prime plus tau double prime x, if this value is taken as x, whole square plus tau double prime y square square root. All values are as a function of h, so we'll get value equal to 1523 by h. And for a safe operation, tau allowable should be more than this value, or equal to, more than or equal to. Tau allowable is given, tau allowable is 88 MPa. Substitute this value here, you will get h should be more than or equal to 17.3 mm. So this is the final answer. But the thickness of plate that is given is equal to 12 mm. At a plate of 12 mm, we cannot weld a 17 mm weld, because the plate is this much thick and weld is more thick. So this weld is not possible. So it means that our whole calculation for these problems are not correct, or we have to redo. We have to change something. What we have to change? We are required to change the type of weld, because this weld, as compared to case number type 5 weld has, for the same area, type 5 weld has double the length. So its strength is almost double. So we can use that weld. So just by changing the color, if we go there, type of electrode is the same. Instead of case 2, we will be using case 5. I'm just with black ballpoint, I'm just changing the values. The area is also doubled. This area will be multiplied by 2, so we'll be getting final area which is equal to 424.4.2 0.2 mm square. Top prime, because area is doubled, so top prime will be halved. So this is equal to this value, 2h divided by 2h. For top double prime, the m is same, x is same, but j will be changed. The value of j is doubled, I think. Yes, the value of j is doubled. So due to double value of j, the final value is divided by 2h. As all the remaining values are divided by 2, so it will be, this whole equation will automatically be divided by 2. When you are solving, you will get exactly same answers. So this final answer will be equal to this value. And when you solve it, h will be 17.3 divided by 2. So h should be greater than or equal to 9 mm. And thickness of plate is 12 mm. All the remaining things remain the same. Value of 150 that we assume is same. Electrode is same. Also moment, there will be no change in moment. Moment will be same. The value of Ju will be doubled, because this because of change of double Ju, value of J will be doubled. This will be same, and the final answer will be 9 mm. So this 9 mm is an acceptable weld. So what is the final answer? What is the pattern? Pattern is all around square weld, because this length and this height is, so the final answer is that we will weld on the back side of this and front side of this. Also electrode, E60XX. Which type of weld? Fillet weld. What is length of weld? 4 into 150 mm or equal to 600 mm. Size 9 mm. And what also length of attachment was required, L was also required, so L is equal to 150 plus 156, which is equal to 306 mm. So you have to write your answer like this, all the answers here. So this is the final design of weld. This is how we design a weld. I hope that you have understood the problem, and this last problem that I will also share on my Google site. This problem is your home study or self-study, not an assignment. The assignment I will give you inshallah tomorrow.